Hey everyone, welcome to another video in chapter 6. In this one, we are taking another step forward, right, in determining whether or not an object accelerates under friction. We're giving this a slightly amped up version, right, slightly more complicated in that it's on an incline now. So you might remember this problem from last chapter. Last chapter, the surface of this incline was frictionless, and I'm keeping the masses the same. We're doing the exact same problem, except now we're going to have some friction on that inclined surface. And so again, we have to determine, as in the previous example, if this system accelerates or not, right? And if it does, at what rate, okay? And what's the tension in the ropes, okay? So, as before, the general strategy was to, once we have our second law equations, solve those equations or solve the equation for the maximum static frictional force, Fs max, right? When we see which value, either that or all of the other forces in that direction, which one's greater? If Fs max is greater, that means friction has overcome all of the other forces and it remains stationary, it remains static, it doesn't move. But if Fs max is less than all of the forces, all of the other forces combined, then it will accelerate. Okay? So let's get to it. So first of all, we have our diagram here, right? I'm not going to necessarily do a true free body diagram, even though I encourage you to do this. For lack of space, I'm going to do it on this diagram here. So in the y direction, for mass A, we have the normal force. We have, I'm going to draw gravity downwards, right? Something like that. That's actual gravity, but I'm going to go ahead and draw it in components. So this component here is MAG cosine theta, right? Remember that angle is also theta. And yes, I know it's cosine 30, but I'm just going to draw theta for right now. Let's see. X direction. For mass A, we have the tension in that string, and down the axis, right, down the incline rather, we have MAG sine theta. Okay. Now in chapter 6, since mass B is 22 kilograms and mass A is 8 kilograms, hopefully your intuition says that B should pull on mass A. Right? If B goes down, mass A moves up the incline. That means that there's a frictional force. Right? Specifically, which direction does it go then? Well, friction always tries to prevent an object's motion. So if mass A wants to slide up the incline, friction must be pointing down the incline. So we draw it that way. Okay? And again, I'll write F subscript F for right now. That's just the force of friction. Okay, so those are all the forces for mass A. Let's do the same thing for B. That's a little simpler. There's just two. There's tension and gravity. Okay, there are no X forces. I also need to draw my axes, right? If this is released from rest, this system B will accelerate downwards and A will accelerate upwards if it accelerates. Okay, so to preempt that a little bit, let's put X and Y like that, and then X and Y like that. Okay. All right, I'm not going to draw the direction of acceleration. Again, we're not sure if it does accelerate. So now is the time to write out the second law equations. Let me do that up here. So for mass A, we have the following. Sum of the forces in the X direction. Our X direction positive is tension, and then minus MAG sine theta, minus, now I'm going to write it's the Fs max. Okay, This is the maximum static frictional force that all other forces must overcome in order to have the system accelerate, right? So I'll write it as that and not simply FF. And that equals m subscript a times acceleration in the x. Sigma Fy, well, that is Fn minus mag cosine theta, right? Hopefully the second law equations so far are a little bit of a refresher, right? A little bit of a review. I'm assuming you've been able to write out some second law equations so far, right? So this shouldn't be anything new. What's this? In the y direction, that should be 0, right? I'm just going to go ahead and make that 0. So mb, we have sigma f in the x direction. Well, that's easy. There are no forces. And in the y direction, our positive is actually down. That's okay. We're completely free to choose whichever direction is positive. And that equals MBAY. Okay. Again, we don't know if it accelerates. I'm just writing MA out of habit. Okay. If I know it may accelerate. Okay. Actually, I might as well take away the subscripts. Whoa, whoops. Because if it accelerates, then that's really the same direction. There's just the one acceleration. Okay. Now, again, the question is Fs max greater than all other forces in that direction? So we're going to solve, let's do this equation. We're going to solve that one for Fs max, right? So solving that should give us tension minus mag sine theta, right? In this case, I'm assuming here there is no acceleration, right? So really, you don't need to worry about that. Treat that as 0 for right now. We're just simply worried about the magnitude of that one. Is that greater than or less than? Yeah, you're right. Greater than or less than the sum of all other forces in that direction. So Fs max, remember, has the expression mu s times Fn, right? The normal force on mass A. And then tension. Ooh, do we know tension yet? Interesting. We're not sure. Tension minus ma, yeah, that's kind of the same thing. So, do we know tension? Can we find a way to get tension? Right? If this is not moving, we can. We can use mass B, right? The y equation, or the y direction for mass B, right? So from there, tension equals mbg minus, 0, right? That's what tension equals, right? And so, just to be clear, we can treat the acceleration as 0, right? We're doing this because at the instant that the system would accelerate, right, at the very first micro instant, the force on block A has not reached the maximum static frictional force yet, right? It's just some static friction. But at a couple more micro instants, that force of friction has reached its maximum, okay? So in that first initial couple micro instants, we need to see if the static frictional force is enough to hold that in place, right? So really at the first instant, right, it doesn't accelerate. You can treat that as not accelerating, right? And that's why we can assume that that 0 and that 0 when we're determining whether or not it accelerates. Okay, so knowing this for tension, we can plug that in right there. So the normal force, how do we get that? Well, we can use the y equation for mass A. Okay, so the normal force there is mag cosine theta. So let's see here. That we have mu s, and then the normal force I just said was mag cosine theta. Is that greater than or less than tension, which is mbg, minus this last term, mag sine theta? All right, now we know everything. So let's plug in some numbers. Oh, wait a second. I haven't told you the coefficients. I would have figured it out soon enough. Sorry. Mu s in this problem, at least that I've created, is 0.5. And if it accelerates, we'll use a mu k value of 0.6. Okay. Wait, I got those backwards. Totally JK. So mu s is 0.6, mu k is 0.5. There we go. Great. So now let's plug in some numbers. Now we know everything. So 0.6, MA we said was 8, 9.81, and cosine 30. Is that greater than or less than the right side, which was 22, 9.81, 8, 9.81, and then sine of 30. All right. So when you do this math, let me look at my notes. We should get 40.78, 40.8, whatever. And on the right side, that total is 176.58. So by far, the maximum static frictional force that's on that incline trying to hold mass A in place once the system is released is drastically not enough. Okay? So all other forces combine to vastly overcome it. And so we have acceleration. Okay? Now that we know that, we can go back and tweak our second law equation right there, right? Namely that term. So I'm going to do that on the next slide. So Fx was tension minus mag sine theta. Now we know that it accelerates, so now it's the kinetic frictional force equals ma. All right. In the y direction, we had the normal force minus ma, what was it, g cosine theta? That equals 0. It's not moving out or into the incline. And for b, 0, the y direction was, we said down was positive. Down was positive for b. So that equation doesn't change, except we have ma. There. Now that we know it does accelerate, we can officially input Fk, and we know for sure that there is mass and acceleration. Okay? And so now it's just a matter of algebra. We have 2 equations and 2 unknowns, right? Really 3 equations and 2 unknowns. Whoops. What happened? Oh, there we go. We have T is the unknown as well as A. Okay, so let's see, to solve for that, let me rewrite the first equation. Let me expand that a little bit. Fk, remember, has the form mu k times Fn, right? And we get Fn from down there. Okay, so we have mu k times mag cosine theta. And that all equals ma times acceleration. All right, so let's see. I'm going to solve for t. That seems a little bit easier. Whoops, that equals. So now that we know it's moving, tension is not simply m b times g, right? It's not simply that. It's actually mbg minus mba. Okay. So now I'm going to take this bunch and plug it in for t right there to turn that equation in terms of a. Oh yes, so we have all this other stuff left over. All right, solve for a, you get a really long expression, but I trust that you can do it. The value for a should be 4.75 meters per second squared, right? And once you get the value for a, you can plug it into either equation. So either plug it in right here and solve for that t, or you can plug it in here and solve for that t. It'll be the same exact tension. So I suggest the simpler equation. So once you plug it in for, say, a right there, you should get a tension value of 111.22. And so if you take a look at this example, or rather this problem, the frictionless version from last chapter, the acceleration value was, I believe, 5.8. And the tension value was, what was the tension value? I forget actually. But, well, let's check it here. The tension was 86.3. Interesting. Interesting. So the tension is less, acceleration is less as well. Sorry, the tension here is greater, the acceleration is less, okay? So again, the same process holds as before, right? The overall strategy is to, once you have the second law equations from your free body diagram, you want to, right here, determine if the maximum static frictional force is greater than or less than all other forces in that direction combined. Okay? If friction is greater, the system does not accelerate. If all of the other forces add up to be greater than friction, then it does accelerate, right? And you can go back and tweak your equations and solve for acceleration and tension if need be. All right? Well, thanks for watching.